This is a review of class on May 6th where we were talking about equilibrium problems and moving on to the next level of difficulty with those. So far in this equilibrium unit, we have said what is equilibrium? Well, we've addressed that question. So equilibrium means that the reactions go both directions. And remember the bucket analogy. So what is equilibrium? The reactions go both ways. Then we've done two kinds of problems, or calculation problems. We did these on Friday, May 1st. Videos summarizing what I'm about to say is on that page, on the homework page on May 1st. So the first thing we did was we introduced the idea of the equilibrium constant, and we did problems involving finding the constant if you were given concentrations, or finding concentrations if you were given the constant. Then on Monday of this week, we learned about Le Chatelier's principle, which was not mathematical. It was, Le Chatelier just means that a system will stay at equilibrium and forever until you subject it to a stress, and then the equilibrium will shift to relieve that stress. And I posted practice problems on that after Monday's class. All right, so today we're going to review the KC calculations where we're going to find concentration, and then I'm going to take that to the next level. We're going to do 3 problems. Here we go. First of all, problem number 3 on this little problem set that I have in front of us. It says for the reaction SO2 plus O2 yields 2SO3, the concentration of the sulfur oxides are 2 and 10, and we want to know the concentration of the oxygen. So you set up your equilibrium expression, Kc. Kc means KEQ, C stands for concentration. So if you see Kc, or if you see me write Kc, I'm really talking about KEQ using concentration. You can also use pressure. We're not going to get into that this year. All right, so KEQ is equal to the SO3 concentration. Remember, the concentrations mean moles per liter. And there has to be a 2, there's a 2 in front, so there has to be a square up here in our equilibrium expression. This is a review of last Friday. Then we have SO2, and that has to be squared, and the oxygen is not squared. Then you plug your numbers in. For the SO3, we're told that it's 2. So where's SO3? It's right here. No, wait, SO2 it says is 2. So SO2 is here. So I'll just put the line in. For SO2, I'm going to substitute in 2, and it's going to be squared. The SO3 is 10. So I put a 10 where the SO3 is, and that also is going to be squared. And the oxygen, we don't know. I'm going to call that X. And there's no square on it because we didn't have any coefficient in the equation other than a 1. And so if you like coefficients, you could put, or exponents, you can put a 1 in there, but it means the same thing. All right, and then the equilibrium constant is 800. All right, so now we need to solve for X. You all know by now that you need to clear this denominator. So we're going to multiply both sides by 4x. Remember, 2 squared is 4, and 4x. So now I have 4 times 800 is 3200. X equals 10 squared, which is 100. This is a common place for people to make mistakes. You divide both sides by 3200, or you divide both sides by 100. Hopefully you said 3200, or at least you were thinking that. And they cancel here, so X is equal to 100 divided by 3200. Be sure you punch that in your calculator correctly. It'll be 100 divided by 3200. And that's 0.03125. And we'll just call it 0.0313 because there are 3 significant figures in this number and that number. So 0.03125 would be 0.0313. Zeros in front are not significant. All right, so that's our answer to the first problem, and that's a review problem. Now we're going to take a look at a different kind of problem. It's the next level of difficulty. And is problem number 4 on this page. And you're not going to have this page, but I put some practice problems on a website, and they all work the same way. Okay, so we have an equilibrium expression again. I'm going to write it on paper so that I can move it around if I need to. So plus I2 yields 2HI. Notice that there's double arrows. All right, so note we have 1 mole of iodine in a 5-liter container. So remember that we have to have these concentrations in moles per liter, or the concentrations are given in something we call molarity. And molarity equals moles divided by liters. So in this case, I've got 1 mole, 5 liters. So it'd be 1 divided by 5. 1 divided by 5 is 0.2, and I'm going to put a capital N. That's what molarity is written as. Capital M means molarity, moles per liter. All right, so I'm going to write down what I'm given. I have 0.2 moles per liter of the hydrogen, 0.2 moles per liter of the iodine, and I don't have any of the HI initially. We know, though, that since this is an equilibrium reaction, that some of the 0.2s are going to react and turn into HI. We just don't know how much, but we know some is. If it was not equilibrium, we would assume that if 0.2 of this reacts, we'd get 0.4 of that, and we'd be finished. But we're not going to have a complete 0.4 because some of this reacts and goes back to that. That's what makes an equilibrium problem, that the reactants turn into products, and then the products, before the reaction is complete, the products react and go back to the reactants. All right, so here we go. I'm going to write this down. This is our initial. Now the initial reaction, the initial concentrations are going to change. So I'm going to write change down. We don't really know how much of the hydrogen is going to react. We know that some of the hydrogen and some of the iodine will react and it'll make HI, but we don't know how much. So we need to find out how much. But for right now, if we don't know it, we can just say X amount reacts. So if X amount of this reacts, we know that this is going, the 0.2 is going to change by X amount. I put a minus there to show that it's going to go down by X amount. Since this is a 1 to 1 mole ratio, then this will also go down by X amount. On this side, though, if I have X amount of iodine reacting, then I should be getting 2X of the HI. You see there's a 2 to 1 mole ratio, so that would be 2X. So the HI is going to go up by 2X. Now in this case, we know that we didn't have any, so if it goes up by 2X, when I actually get to equilibrium, I'll write equilibrium down here, these are going to be the equilibrium concentrations. When I actually get to equilibrium, the HI will be just 2X because it's 0 plus 2X, which just equals 2X. The iodine will be 0.2, but we lost X amount, so at equilibrium it would be 0.2 minus X. And the hydrogen, so this goes here, this goes here. The hydrogen, we started with 0.2, and it went down by X amount. So at equilibrium, I'm going to have 0.2 minus X for both of these, and the reason they're the same is because we started with the same amount. It's a 1 to 1 mole ratio, so the same amount reacted or changed, and we end up with what we started with minus however much reacted, which we still don't know, but we're going to figure that out in a minute. Okay. Now, moving on, we need to solve for X. To do that, we're going to need to set up an equilibrium expression, just like we did a minute ago. So remember how we did products divided by reactants? Products divided by reactants. So we have the equilibrium constant, KEQ, or Kc, is going to equal the HI concentration. These brackets mean moles per liter, and that's going to be squared because of that coefficient. The H2 multiplied by the I2. It's the products divided by the reactants, everything raised to their coefficients. So we end up with, at equilibrium, we know that the HI was 2x, so that'd be 2x, and that'll be squared, divided by 0.2 minus x for the H2, and 0.2 minus x for the I, it's supposed to be I2, and that equals the equilibrium constant, which it tells us in the problem is 64. And there's a couple different ways you could do this. Sometimes these problems require a quadratic equation. This one could be worked with a quadratic equation. I'm going to go ahead and leave our problem. We're supposed to be finding the equilibrium concentrations, and we will do that. So I need more space. So here we go. So we have this set up. We could use the FOIL thing on this, where you have first times outside times in times last. So I'm just going to put over here on the side, you could say this is equal to 4x squared, because 2 squared is 4, and x squared is x squared, divided by 0.04, that'd be firsts, minus 0.2x, and then another minus 0.2x, the outside and then the inside, so that would be minus 0.4x plus x squared, and that equals 64. Well, then you could rearrange this, put it in standard form, and I'm not going to actually go through that process because there's a simpler way to do this particular problem, and then we'll do a quadratic in a minute. All right, so here's how the simple way to do this one. You might notice that this one is a square, and this are the same thing, so that's a square, and you could take the square root of that. So if we just took the square root of both sides, I would end up with 8, because the square root of 64 is 8. The square root of the numerator here would just be 2x, because the square root of 2x quantity squared is just 2x, divided by the square root of 0.2 minus x quantity squared, so it'd just be 0.2 minus x. So now we have a simpler problem to solve. We still need to clear the denominator, so multiply by 0.2 minus x. They cancel over here, so now I have 0.2 minus x multiplied by 8 equals 2x. You will recognize that this is a distributive property application. So we have 0.8 times 0.2, which is 1.6, minus 8 times x, 8x, equals 2x. Now we add 8x to both sides to get the x's all combined. So I end up with these canceling, and 1.6 is equal to 10x. Now to solve for x, final step, divide by 10. 1.6 divided by 10 is 0.16, and that is equal to x. So now let's go back up to the top. X is 0.16. I'll write that out up here so we can remember. X equals 0.16, okay, that we solve for. So now go back and find the equilibrium concentrations. If x is 0.16, what's 2x? So the HI is 0.32, and that is the equilibrium concentration of the HI. If x is 0.16, what's 0.2 minus x? So 0.04, and same thing over here. So those are the equilibrium concentrations of the H2 and the I2. All right, so quick review. What makes this problem different is that you're given the initial concentrations, not the equilibrium concentrations. Initial, not equilibrium. When you're given the initial problems, you have to do what we call an ICE problem. It's an ice box. So you got ICE, initial, change, equilibrium. You write down what you're given initially. You figure out how to express the change in terms of x, and then write the equilibrium concentrations. Then plug into your equilibrium expression and solve for x. After we solve for x, plug back into what we said the equilibrium concentrations will be, and then you're finished. All right, one more example. going to do one that does require the quadratic equation. I didn't go back and show you the answers. That was number 4. There's your answers. Okay. Number 10. We're going to take a look at number 10 here. So we have this equilibrium, PCl5, yields PCl3 and Cl2. And that's an equilibrium, so we have 2 arrows. All right, we know the initial concentration of the PCl5 is 0.05. So the initial is 0.05 molar. We didn't need to find the molarity because it was already given to us. If we're not given the molarity, then we have to actually calculate moles divided by liters. Okay, so that's the initial concentration. We know it's going to change by some amount, and there will be some equilibrium concentration. And again, the key word here is initial. If we're given the initial concentration, then we have to use the ICE method, the initial change in equilibrium. All right, so we don't have any of the PCl3 at the beginning. We don't have any of the Cl2 at the beginning. We know that some of this will react, but since it's equilibrium, not all of it will react. So we lower it by some amount that we don't know. We also know that there is a 1-to-1 mole ratio. So we know that if X amount of this reacts, then the same amount will be produced because of the 1-to-1 ratio. Same thing here, 1-to-1. So that's going to be X. So these are both going to be going up by X amount, and this is going to be going down by X amount. So when you actually hit equilibrium, you're going to have 0.05 minus X. Because you started with 0.05, X amount reacted, so what you have left is whatever you started with minus the amount that reacted. Over here we know that we had 0 to start with and X was produced, so at equilibrium we're just going to have X. Same thing here. We had 0, X was produced. At equilibrium, we're just going to have X. I'm sorry about that. Phone call shuts off my webcam, so it'll take me just a second to get that back. All right, now I'm back. All right, so same thing over here. We didn't have any, so we had X amount produced, so you have X. All right, now we know the equilibrium constant in this problem is 0.042. So 0.042 is our equilibrium constant. Okay, I'm running off the screen here. So 0.042 is going to equal the products. In this case, it's PCl3 multiplied, those are concentrations, multiplied by the Cl2 divided by the PCl5. So the PCl3 we said was X, and the Cl2 is X, and the PCl5 is going to be 0.05 minus X. Once again, 0.042 was the constant that was given in the problem up here. All right, so here we go. I'm going to go kind of fast on solving this equation because of the time in the videos. You can always rewind me. All right, so X times X is X squared. 0.05 minus X is on the bottom, 0.042. Multiply both sides by 0.05 minus X because you need to cancel the 0.05 minus X on the right side. So boom, boom, out of there. Equals X squared. Okay, 0.05 times 0.042 is 0.0021. So I'm doing this times this, 0.0021 minus 0.042x. Now I like to have my standard quadratic form set up like this. Ax squared This is how Mrs. Coble taught me when I was a freshman in high school. So I'm going to put it in that format, which means I need to put the x squared. I want the x squared on the over here. So I could subtract x squared, but then that's going to give me a -1 for my a term, and I just like a +1 better. So I'm going to put this and this on that side. So I'm going to subtract 0.0021. I'm going to add 0.042x, and that's going to equal x squared. So what I have here, this minus that is 0. And that plus that is 0. So I end up with x squared, and I'm going to have to add the 0.042x, so plus 0.042x. Sorry, I got off screen there. Put that back up, give you a second to catch up. All right, and then I'm going to subtract the 0.0021, so minus 0.0021. All right, so there's my standard form quadratic format. Ax squared, 1x squared. Bx, 0.042x. C is -0.0021. All right, you will remember from your math class, x is equal to -b plus or minus the square root of b squared minus 4ac. And that's all divided by 2a. So I'm going to plug these numbers in and solve for x. All right, so here we go. Equals. So the b term is 0.042. So it's going to be -0.042 plus or minus the square root of the b term, 0.042 quantity squared, minus 4 times 1 times -0.0021. Negative because of the negative sign here. And that's all going to be divided by 2. All right, so I'm going to do what's underneath. I'm going to put my calculator up here so you can see what I'm doing. And I'm going to do what's underneath what's called the radical, the square root sign. So 0.042 times 0.042, that's squared, equals. Now you notice that we've got a minus and a minus. That's a plus, isn't it? So it's going to be minus 4 times 1 times -0.0021. So those three numbers together are going to give you a negative term, and then minus and minus is a plus. So I'm going to say plus, my answer plus 4 times 0.0021 equals. Now that's the number that's under the square root sign. So now I have -0.042 plus or minus the square root of 0.010164, and that's going to be divided by 2. All right, now I'm going to take the square root of this number. So to do a square root, you can raise to the 0.5 power, because the square root just means simply raised to the 1/2 power. A cube root would be raised to the 1/3 power, and so on. So 0.5. So 0.1008 is under the square is what this equals. So now I've got -0.042 plus or minus 0.1008, and all that's going to be divided by 2. All right, so going on down, -0.042 plus 0.1008 equals, then go ahead and divide by 2 equals, so I get 0.0294. Or, there's another answer here because it's plus or minus, so I have -0.042 minus 0.1008 equals, and then divide that by 2, and I get -0.07. Okay, now if you go back and look at, take our two answers, I'm going to go back, I'm going to write them up at the top of the page, which you can't see here, but I'll bring them back up here. We know that our x is equal to 0.0294, I'll just call it 0.029, or -0.71, or 0.071. All right, so those two answers are both valid mathematically, but in chemistry, one of them doesn't make any sense. Because if you put the negative 0.071 as a concentration, that would be just kind of silly because you can't have a negative concentration. You don't have a negative mass. Remember, that was one of the problems with the phlogiston theory back in the fall, that the negative mass threw that phlogiston theory out the window, even though it was based in experimentation. So we would have to say that x is equal to 0.029. So x equals 0.029. 0.029. Actually, we'll put circles around those because those are the equilibrium concentrations of the PCl3 and of the Cl2. Since x equals 0.029, 0.05 minus 0.029 is 0.021. And that is the equilibrium concentration of PCl5. So that's your final answer to the question. All right, so again, this was an initial, the equilibrium, the concentration that was given was an initial concentration. When it's an initial concentration, you need to set up your icebox format. You write down what you're given. You know some of it reacts. Then you write down what would be there at equilibrium, even though we don't know at this point what reacts. We know that X amounts reacts, and there's a 1-to-1 mole ratio, so X will be produced. So set that up. Then write your expression down, products divided by reactants. Put in your equilibrium concentrations and solve for X. Sometimes you have to use a quadratic, sometimes you don't. In this one, we did have to use a quadratic. Okay, so when we solved for a quadratic, we knew what X was. One of the answers in the quadratic doesn't make sense in chemistry because you can't have a negative concentration. That doesn't mean that a negative answer is always wrong, but a negative concentration will be wrong. And sometimes when you take a negative number and you plug it in up here, it makes sense, but not this time. All right, so 0.029 was our equilibrium concentration for the PCl3 since we defined it as X. Same thing for Cl2, and then 0.05 minus what X was equal to was the PCl5. Then usually your last step is to check your answer, see if you got it right. So you go to number 10. The answers they gave were the 3 sig figs instead of 2 sig figs, but we had 0.029, and in my case it was 0.0294 instead of here's my calculator, 0.0294 instead of 0.0295, but we would say that that was close enough to be within the tolerances of rounding, and so we got the problem right. 0.0205, 0.021, same thing. Okay, that is the end of this little summary of class. We are going to meet on Thursday for new content. All right.